Okay. Hello, everyone. Can everyone hear me clearly?
They're muted.
Okay. So welcome to the CLiCC Webinar series. And so for those of you who are not quite familiar with CLiCC, so CLiCC stands for Chemical Life Cycle Collaborative. So here at UC Santa Barbara, we work with US EPA to develop a tool to screening the chemical life cycle impact. So in this webinar, we are going to introduce one of the modules in CLiCC, which is about chemical life cycle inventory. So in this webinar, we're going to cover basic knowledge of life cycle inventory and the method that we are using to develop a chemical life cycle inventory database. So if you are interested in the development of LCI, I hope so. I hope after this webinar, you will get some basic idea about what we are doing for chemical life cycle inventory database. And also, I hope this can help you to make your own LCI database eventually. So before I get started, I just want to introduce everyone here in this room with me. So we have Marvin with me, and Dingsheng, Jeff, and myself, Runsheng. So in this webinar, I'm going to introduce the background of this webinar, and also Jeff is going to talk about some of the method detail about this project, and then I will show one of the demo of our database right now. So again, if you have any questions, so feel free to type in your question in Zoom. And also, since this webinar is recorded, and you are also welcome to email us about your question about our project, and also the question about the overall CLiCC project. And I will provide an email address where you can send your question to. So how can I select? Okay. I think the keyboard is not working. Which
This.
Okay, this side. Okay, good. So before everything, I just want to remind you that we are holding this series webinar for CLiCC project. Since this webinar is the first one, so I just want to remind you we are having 2 more webinars after this. So the upcoming next one is at September 30. We're going to talk about QSAR module, release, and fate and transfer module. And the last webinar is going to happen at October 7th. And at that webinar, we are going to introduce the predictive life cycle impact assessment module, exposure toxicity module, and the uncertainty module. And again, all of this webinar, I just want to remind you that all of this webinar will be recorded online. And if you can make one of this webinar and you are still interested into it, so you are welcome to watch the video later. So in this webinar, we're going to introduce the life cycle inventory module in the CLiCC project. So I know most of you are already pretty familiar with the CLiCC project, but just to recap it, the main point of the CLiCC project is to deliver a tool to screening the life cycle impact for new chemicals. And so to do that, we have a lot of modules to help the user to model the environmental impact of chemicals in different phases. For example, here we have one of the modules that dealing with calculating the release of the chemical during the use phase. And also after the use phase, we have another module to calculate the fate and transport of the chemical. To calculate. Okay.
Sorry, someone just joined, and I'm going to mute him or her.
Okay, so after the use phase, we have another module to deal with the fate and transport, that is calculating the mitigation of chemical between different environmental compartments. So, but about everything, the first phase is chemical production, right? So, and this is where the life cycle inventory project is located. So we need to estimate how much raw material is required and how much emission is generated, and then how much energy is required to produce the user's input chemicals. And so to do that, we do rely on some of the external databases, for example, equivalence. But for the majority of the parts of this, sorry. Sorry, just one moment. Dingsheng, how can I turn this back? Okay, I have to press this harder, I think. Okay, sorry about that. So, above everything, there is a lifecycle inventory database as our background database. And to do that, although we do rely on some external database, But for the majority part for this LSI module, the task is to build our own LSI database. And this database, to serve the purpose of our project, must include a lot of basic chemical life cycle inventory information, right? So when user input a new chemical and they tell us, okay, what are the raw materials of making this chemical? And we will find them in our database and populate the life cycle inventory for the new chemicals. So if you think about this, this is actually a very ambitious, goal, because given the background of the CLiCC project, we are going to deal with new chemicals, and for the most of the part, for the most of the cases, we really know very little information, because the goal of CLiCC is to generate rapid estimation and for chemical in life cycle based on very limited information. So many times we only know the chemical name. So we need to build a database so that we can search the default life cycle inventory for the very common basic building blocks databases. Building blocks chemicals. So in the next 50 minutes, we would like to go over the detail of this project with you. And again, if you have any questions, so feel free to ask us. So, but before everything, I want to just recap that what is life cycle inventory. So I know most of you have a pretty good understanding about LSA, but I just want to mention that life cycle inventory is a building blocks for life cycle assessment, and usually we call it LSA. And it is a fundamental part for LSA, where we record all of the input and output on life cycle basis. So for myself, I would like to consider life cycle inventory as a tree. And because of the fact that LSA is not only recording the direct inputs and outputs for some products. So for example, in this graph, each of the nodes is representing one of the product. And in our case, those products are chemicals. So I'm just gonna say chemical from now on. And it's not only recording the direct input and output, but also all of the upstream inputs as well. So it could have a lot of branches. So for example, if we want to generate the life cycle inventory for the product in this red color, which is located in the center of this tree, and in this case, it requires two inputs, and each of these two inputs also requires another tier of two inputs, and those inputs also require another tier of inputs. So in this case, this is just a binary tree, right? So it's pretty simple, and each of the products only require two inputs. But in real world, we really, each of the products each of the chemical might require a lot of inputs. And so this tree could be very complicated, and the tree can grow very faster because, there might be a lot of tier above the desired product. But that brings a very important question in LSI, is that we need to select a cutoff boundary, right? If we do not, the tree can grow infinitely, right? So if we scale the quantity of every node here after the red nodes to be producing 1 kilogram of the product in the red node, so everything is serving to produce only 1 kilogram of the desired product. So you can quickly find out that for most of the nodes at the edge will have very small quantity, right? And so we could cut them off from the tree, and then we can stop growing from there, because the quantity of the nodes that are on the edge of the tree could be very small, and then it might contribute very small in the final life cycle impact assessment. So in our case, those nodes are on the edge. In our database would be the basic building block chemicals like chlorine, methane, and ethanol, which will be used very commonly. And we will show an example later. So that's the basic concept of life cycle inventory. Again, it is a very crucial building blocks in LSA as well as in our project. So many of you might already have a very good understanding and experience of using life cycle inventory database. And you might ask, okay, why do we create our own database instead of using the existing one out there? For example, like equivalence have a very good life cycle inventory database, and the US LCI has a United States life cycle inventory database, and also in Gabi there are a lot of default databases embedded in their software. So first of all, obviously the number of the chemicals in those databases is very limited. So there are less than 300 organic chemicals in organic chemical LSI available out there. So when we come to the situation of creating a tool to populate the LSI for new chemicals, we need a database contains more chemicals, obviously. So the number of the existing chemical LSI is limited for us. And also, most of the databases are using very crude assumptions For example, in some of the databases, they just assign default selectivity for for every production of the chemical, and most of the time is 95%. And it's a okay assumption, but we want to do better, and we want to utilize the best of all of our users' input, which we will elaborate later, and what is the meaning of that. And also some of the database just for the heat requirement, some of the databases just give an average number for each chemical in their database, which is obviously not true, because some of the chemical production must require a lot of more energy than some basic chemical synthesis. So we also want to do better on the heat requirement in our project. And then lastly, most of the databases are using are commercially available, and so given the situation that CLiCC tool is going to be a public open tool, so it's not ideal for us to use some commercial database. And again, those existing databases cannot provide enough information for the rest of the module in CLiCC. So that's why we building our own database, and we also covered part of the knowledge about LCI. But talk about the chemical LCI. So there are three major components in the chemical LCI. So these components are raw material on the left, heat and energy, and heat is also part of the energy, and also other components, for example, transportation and chemical plants. So for example, the raw materials are the chemical inputs used in the production of the desired chemical. So in other words, the reactants those are the reactant in the chemical reaction. And at this point in our project, we spend a lot of effort to find the raw materials requirement in each chemical production process. And because we need to know what are the raw materials and the quantity of the inputs for producing 1 unit of the chemical. And the second part is energy requirements, right? So energy includes heat and electricity. So because you can imagine that some of the reaction is endothermic, and it might require a lot of energy to let the reaction start. So heat means the heat requirement is chemical reaction, and the energy refers to and also part of the energy refers to the electricity in the reaction, because you can imagine in the chemical plant, some of the devices might require electricity, to let the reaction start running. So in most of the cases, heat and electricity requires a requirements is pretty difficult to obtain, and at some level it's pretty difficult to model. So at this point, we are still working on about the heat energy requirement, and very soon we will come up with a better methodology to estimate the heat requirement in chemical production. And the last component is others. So believe it or not, so transportation is also part of the chemical LCI, and also chemical factory is also part of the chemical LCI, because chemical factory, for example, has a land use occupation, and those land use occupation also have impact score in the final life cycle impact assessment. So those components are also part of the life cycle inventory. So that's the three components we will consider in our project. And just in a little bit of detail, so making a chemical LCI is actually modeling the situation for a chemical plant, right? So we want to simulate what is happening in the chemical factory. And here we have a very simplified version of a chemical plant workflow. So where we basically consider two things. The first thing is the synthesis process, which has happened in a reactor, and also the second part is the separation process, which is obviously happening in a separator. So we use this workflow to guide us when we creating a chemical LCI. We want to use this graph to remind us, and also to show what are the basic components that we're considering when we're creating this chemical database. So for the first part is the chemical synthesis, which is happening in reactor. So obviously there are three components for the three inputs for this for the reactor. Obviously we must have the raw material. We need to know the name of the what are the raw materials and the quantity of them. And also, as I mentioned earlier, it requires energy inputs for most of the reaction to happen. And because some of the reacting is very requires a lot of energy to start. And also electricity is also part of it, because some of the devices in the chemical plant requires you to have electricity as input. So but for the separation process, we don't have any raw material there anymore. The only purpose of separation is that the input mixer after this reactor will go into the separator. And the purpose of separation is to divide the mixed chemical after the reaction. In this mixture, we have part of the desired products as well as some unreacted raw materials and some byproducts and co-products. And if we want to get out the desired products from this mixture, we need to separate and separate those chemicals, and also some of the chemicals, some of the output from the reactor will be recycled back to the reactor, and also another part of the mixer will become waste, and the final output will be our desired chemical output after the reactor. Again, for separation process, we need a lot of energy. We need a lot of heat and electricity to start the separator and let it running. So we use this workflow as the guidance of our work in the LCI project. Again, we have 3 major flows here. Just keep in mind material, heat, and electricity in our workflow. So we just want to mention that before we created this database, we also did some analysis on how much each flow I just mentioned there, material, electricity, and heat, how much of each of them contribute to the final life cycle impacts. So by doing this, we can prioritize our work, and also most importantly, we can understand which flow we should spend the most efforts on, so that we can benefit the most by reducing the uncertainty of that flow. So you can imagine we do have some uncertainty in the CLiCC project, but we want to spend our most effort on some very important flows that contribute the most in the uncertainty. If we can reduce the uncertainty of that flow, we can reduce the overall CLiCC uncertainty at the most. So if what we did here is just we selected 16 chemicals as a case study, and we calculated their impact on the impact score on global warming. So on one side, we took this 16 chemicals, and we get all the full life cycle inventory for those chemicals. Those life cycle inventory include raw material, electricity, heat, and also other components. So everything I just mentioned there. And on the other side, we selected exactly the same chemicals and exactly the same 16 chemicals, but we only took the raw materials life cycle inventory from the full life cycle inventory. So on the other side, we have the same chemical, but in the life cycle inventory of that chemicals, we only include the raw materials, because we want to compare, if raw material took the majority part in the final impact score. So, and we calculate the LCIA, life cycle impact assessment, for both of these 2 data sets. So again, on one side is full LCI, and another side is a partial LCI, which only include the raw material. And we compare the differences between them. So here is the result in this graph. So as you can see here, the y-axis is the percentage differences, and the x-axis is the chemical name. Out of the 16 example chemicals, only 3 of them have a difference higher than 30%. So of course, the full LCI result will always be higher than the partial LCI, because it contains a lot more stuff there. So this is meaning the full LCI is 35% higher than the partial LCI. But as you can see, for most of the chemicals case study we did, they are less than 30%, meaning so if we only include the raw material in the LCI, the difference is only is about 30% or even less. So this indicates that we could focus our effort at this point on raw material first. And if we could estimate a raw material requirement in a good quantity, the result of our LCI database could be very promising with a very acceptable uncertainty. And I'm not saying that heat requirement and other components are not important. I just want to mention that at this point, we spend the most effort of our project to collecting very accurate raw material result to build this LCI database. So that really formed our goal of this project. And at this point, I just mentioned we focus our effort to develop a database that contains the manufacturing information for thousands of chemicals. And this database, is only including raw material requirements at this point. We will add heat requirement and the electricity and also other components into the database later after we get a very accurate result for the raw materials. And the strategy for our user and other CLiCC module to use this database is that for any new chemicals, since they are new chemicals, they are likely not exist in our database, right? Because our database only contains about 1,000 chemicals. It is large size, but still it is limited. We cannot cover every chemicals in the world, especially for new chemicals. And they are not likely to exist in our database. So the user will need to provide the direct raw materials. So what are the chemicals that is making this desired chemicals, which is chemical C in this equation. This is the desired product, and they must provide the name of A and B. And then we will have a background database, and we will look up the LCI of A and B, and hopefully this A and B will exist in our database. And if it's not, user need to provide another tier of input until they touched our database. So because our database contains a lot of basic chemicals, and for most cases, this A and B will directly contains in our database. So it shouldn't go to too many tiers after the direct input. So to build this background database, we need to have our database to have some certain features to achieve this goal, right? So because our user would only able to provide a unit process information, so we need to have this database to contain a lot of basic chemicals, and also we need to make sure that all of these basic chemicals are linking all the way up to some building blocks chemicals. Say in this case, in this graph is one of the example of our current database. Is just part of it. It's not every chemical that we have in the database. And for example, some of the user's input chemical could be very complicated chemical at the edge of this graph, and they require some input, and we need to make sure that all of the input from the user's chemicals must be linked all the way up to some very basic chemicals. Here we often call these chemicals as building blocks. And for example, in this graph, it's chlorine, and this is definitely part of the building blocks. It has been referred many times because it's very common chemicals, and also water, benzene, ethanol, methanol are also very common building blocks chemicals in our database. And we want to make sure that we collect very accurate building blocks chemicals LCI information, so that we can make sure for most of the cases in our database we have a very good output from our database. So one of the over the summer, one of the biggest achievement of this LCI project that we built a background database to generate chemical LCI, and we have collected more than 1,000 chemicals LCI information, and those chemicals are very common and dominant chemical in the market, and it has been used very often. And we collected 1,000 chemicals unit process information, but we make sure every chemicals are linked together so that we have a comprehensive database, and by doing this we can make sure users' input will not go to a dead end, right? And we cut off this our database selection at some building blocks, as I just mentioned. It is chlorine. There are chlorine, water, and ammonia there, for example, and we want to collect very accurate LCI there. And this is just a skeleton of the database, right? We need to fill in the number of the LCI of the LCI. So the LCI numbers, the result of the LCI are calculated. Well, I should say the result of the unit process is calculated under 3 different scenarios according to the user's input. So we want to utilize the most for our user's input, and if our user can give us slightly better input, and instead of just the chemical name, for example, if they know some level of detail about the unit process, and we can definitely generate better LCI result. And sometimes when you're creating this database, it is trash in, trash out, but you give us a better input, will definitely generate a better result for our user. So I'm going to give the speaker to my colleague Jeff, and who is coming from a chemical engineering department, and he's going to introduce at some level the details about our methodology, about how do we set up these 3 different scenarios for our user, and how did we calculate the number in the life cycle inventory. So I'm going to give the microphone to Jeff right now.
Thank you, Runsheng. Okay, so as Runsheng mentioned, the available methods we have to generate lifecycle inventory data really depend on the user's knowledge. For instance, if you're a chemical manufacturer and you have detailed process knowledge, That's obviously the most favorable scenario. And if you have that detailed process knowledge, you can calculate life cycle inventory easily from the material flows directly from your process. Now, we realize a lot of the interested parties in the CLiCC tool will not have this level of process knowledge, so we have a couple different methodologies as well. So if the user has knowledge of the chemical kinetics for the chemistry of interest, we've been working on developing a kinetics-based approach that can calculate life cycle inventory information, primarily material flows into and out of the unit process under the very best case scenario. And if you don't have information about kinetics, if you only have knowledge about the chemistry of interest or even just the chemical of interest, we've also developed a stoichiometry-based approach that can use assumptions about the efficiency of raw materials usage to generate life cycle inventory data. So as I mentioned, we realized that most people will not have detailed process knowledge, so we're going to focus on scenarios when you know something about the kinetics or when you only know the chemistry or the chemical of interest. Now with this database we're building, if you only know the chemical of interest, if it is within the database, then you can search for the chemistry if you know the chemical. So all three of these methods only generate gate-to-gate lifecycle inventory information, so it's only about the specific unit process. But for the CLiCC project, we desire cradle-to-gate lifecycle inventory information, which means we need the lifecycle inventory information of the inputs to the process. Now, as Runsheng mentioned, there are possibly many steps upstream of producing the chemical you want, maybe even going all the way back to the chemical feedstocks. And gathering all this information is really a daunting task. However, with this database we are generating, it really makes generating cradle-to-gate lifecycle inventory a much more feasible task. So in this database we're developing, we are collecting information about the chemicals, the associated chemistry, kinetics when available, and also lifecycle inventory information. So let's go over some of these approaches. So the first approach I want to talk to you about is the stoichiometric approach. So stoichiometry is just a fancy way of saying molecular counting in chemical reactions. So it tells us, stoichiometry tells us how much of a given reactant is consumed and how much of a given product is generated in a given chemical reaction. So if we know the stoichiometry, we can, if we know how much product we want, we can calculate the requirements of the other species. So if we consider this chemistry, this fake chemistry given here, A plus 2B goes to C plus 3D. Let's suppose we want to make chemical C. We want to make one molecule of it. The stoichiometry tells us that we need one molecule of A and 2 molecules of B. It also tells us that we make 3 molecules of D, even if it's something we don't want. And this is true of any process operating this chemistry. These are the facts. So if we know how many molecules we need to make a given molecule of desired product, we can back calculate the mass required to generate 1 kilogram of product. So in general, chemistries are more complex than the one I just showed. They often involve multiple reactions that generate the desired product, as well as undesired byproducts and wastes. So an example is shown here, A plus B goes to C and A plus C goes to D. So let's suppose we want to make C. How much A and B do we need? How much D are we going to produce? The truth is, with only stoichiometry, we do not have enough information to answer that question. We really need more information, particularly about reaction selectivity. So reaction selectivity is sort of like a reaction efficiency. It essentially tells you how much of your limiting reactant, how much of your key reactant is going to make what you want to make, as opposed to making byproducts and waste. Mathematically, the selectivity is defined as the molecules of desired products formed divided by the molecules of your limiting reactant consumed. So this is really what we need to calculate life cycle inventory information. However, in the stoichiometric approach, we're assuming that the only thing we know is the chemistry involved, or maybe just the chemical involved. So we're not going to, in general, have information about the selectivity. So to overcome this, we're just going to assume that the selectivity is about 95%. So we're going to assume about 95% of the limiting reactant is going to make what we want, as opposed to making what we don't want. So we can sort of use this estimation as a surrogate for better process information. So going back to this more complicated example, we can briefly run through how we calculate information. So the raw materials required can be calculated as the production rate of your desired product, which a user would specify. You know, I want to make 100 million tons per year of, you know, chemical X or whatever. and then that divided by the selectivity of that product, which for this case, we're going to assume is 95%. So this very simple equation, a really simple assumption, we can get an estimate of raw materials required. Similarly, we can calculate the amount of a byproduct or waste that's generated as the amount of raw materials required times the selectivity of that byproduct or waste. So the fraction of the raw materials that go to that byproduct or waste. We can do some simplification. We see the amount of byproduct generated is equal to the production rate of the desired product, which once again we specify, multiplied by the selectivity of the byproduct, which we can find from the selectivity of 95% assumption, and then all of that divided by the selectivity of the product, which once again we assume is 95%. So as we see with stoichiometry and a simple assumption about selectivity, we can calculate an estimate of all the material flows into and out of a unit process. So that was the stoichiometric approach, and it does use that assumption. In general, we would like more realistic life cycle inventory data if we can get it. So what you really need for that is a more accurate reaction selectivity. The difficulty is you really don't know the selectivity until after you've designed a chemical plant. Furthermore, no two chemical plants are the same, which means you really can't take a selectivity from one plant and use it in another plant. In addition, you may be considering multiple synthesis routes. There may be more than one chemistry that can give you your desired product, in which case you'd have to design two chemical plants, which would be really bad. So all of this leads to an interesting problem. You really can't obtain selectivity information before you design a chemical plant, which means it's really difficult to conduct life cycle analysis very early on in the design phase, which is when you want to do it. Furthermore, it's difficult to redesign a chemical plant if selectivity or life cycle results are unfavorable. So where we are, we really want more accuracy than assuming a selectivity of 95%, but we don't want to design a chemical plant to get that information. So to overcome this, we've been developing this chemical process design module. This is based on a strategy for obtaining an upper bound on selectivity, so the highest selectivity you could ever hope to achieve, completely independent of process design. And with this upper bound on selectivity, we can obtain realistic production numbers for early life cycle analysis. So, or rather, we can find production numbers based on the very best case scenario. Furthermore, this upper bound on selectivity provides a benchmark during the process design phase, which is very useful for designers of chemical plants. If you know if you're close to the maximum selectivity, then you can stop seeking improvements. So this module does require more inputs than just the purely stoichiometric approach. You need the chemistry involved, so you need to know the components involved in the associated reaction. You need to know the reaction kinetics, you need to know some basic chemical physical properties, and you need to know some very basic process constraints. But with all this information, you can get target selectivities, you can get the amount of raw materials required, you can get the amount of byproducts, co-products, and waste formed, and you can also determine how much waste is avoidable. So all of this is done based on this principle called the cfstr equivalence principle. Without going into the really nitty-gritty details, essentially what this principle allows us to do is it allows us to represent any possible arbitrary process you could ever hope to consider using a single mathematical model. It does this using a small number of traditional reactor types combined with perfect separations arranged in a specific way. But basically, it allows us to, instead of investigating every single chemical process you could think of, it allows us to essentially optimize a single model. So this model encompasses all possible plant designs, even those which cannot be imagined. So we only have to investigate one model, essentially, instead of investigating a nearly uncountable number of potential models. So with this principle, we can obtain an upper bound on chemical selectivity, which we can use to calculate life cycle inventory data under the very best case scenarios. Furthermore, a lot of the work I've been putting into this project involves imposing practical process constraints on this model. So basically, this is to prevent us from investigating a process that has unrealistically large flow rates, for example. So we want life cycle inventory data results, but we don't want anything unreasonable. So we can achieve that with these practical process constraints. So as a very brief example, I have a comparison of two different synthesis routes. This is for making a chemical called phthalic anhydride. It can be made in a couple different ways. One is from oxidizing naphthalene, and the other is from oxidizing orthoxylene. In the plot shown on the right, the naphthalene chemistry is represented by the orange color, and the orthoxylene chemistry is represented by the blue color. So as I showed before, we can calculate the amount of byproducts and waste generated when making a chemical. For both of these chemistries, in making phthalic anhydride, you also generate quite a significant amount of carbon dioxide, which everyone knows is something we in general want to try and minimize. So with this methodology we've developed here, we can find basically the minimum amount of carbon dioxide that we must produce. The minimum amount that we must produce for each of these given chemistries, and we can compare that to some traditional reactors. So the solid orange and blue lines in this plot on the right represent the CO2 production rate of some traditional reactors. The x-axis here is conversion of limiting reactant. So this is essentially the fraction of your limiting reactant that has reacted to become something. So as we see, as we react more of our limiting reactant going from the left to right-hand side of the plot, we generate more and more carbon dioxide, which is something we want to try and avoid. The data markers on this plot, the orange squares and the blue circles, represent the life cycle inventory results for carbon dioxide under the very best case scenarios. So this essentially tells us the minimum amount of CO2 that we must produce using either of these chemistries. And what we see from this is that for both of these chemistries, the minimum amount of CO2 that we must produce, especially at higher conversions, is significantly lower than what we would see in a traditional reactor type. So this tells us that there is a potentially significant possible reduction for CO2 production in the phthalic anhydride chemistries. So there's a fun little example at the bottom of the screen, this table. It shows the CO2 production for a process producing 75 million pounds per year of phthalic anhydride. Now what this tells us is that for the orthoxylene chemistry using a traditional reactor, we will generate about 137 million pounds per year of carbon dioxide at around a conversion of about, I think, 95% or so. However, this chemical process design module tells us that we could potentially reduce that up to 57 million pounds per year down to about 80 million pounds per year of CO2. Similarly, for the other chemistry, we see that a traditional reactor will produce about 122 million pounds per year of carbon dioxide, whereas we could potentially reduce that down to 100 million pounds per year. So hopefully what I've shown you is that we have a couple of different ways to develop lifecycle inventory data depending on the amount of information the user has. But also hopefully I showed you that byproducts and wastes are inevitable. They're not something you can avoid. Furthermore, some reactors, some chemical process designs are closer to the maximum possible selectivity and will have less byproducts and waste than others. But with this methodology we've developed here, we can calculate life cycle inventory data under the very best case scenarios. We can determine how much waste is avoidable, and we can also use this methodology to compare different chemical synthesis routes, which would be very useful in the design phase or even prior to the design phase of building a chemical plant. So with that, I will turn it back over to Runsheng.
Okay, thanks, Jeff. And so that was part of the methodology that we are using in our current LCA project. And hopefully after that, you will get some idea about what we are doing and what methods we are using to generate the number in the life cycle inventory. And but just to recap that, so we mentioned that 3 different scenarios. When user have a detailed unit process information, we will just use it. And the second level is that if user can provide some kinetics data for the chemicals that they are desiring to produce, and we can generate some best case scenario unit process for our user. And the last scenario will be the user only knows the name of the chemical. I apologize. This should be to only know the name, and so that we can we will fill in the number based on stoichiometry. But all of these 3 scenarios requires us to have a background database to support the data requirement. And so again, so over this summer, we one of the biggest achievements is that we built this database, as I just mentioned, and we collect the data from industry report, and we fill in the number, in the database internally using chemical stoichiometry. And so although the accuracy of the output from the ISI module would decrease from the very top when user have detailed unit process, and it's gonna keep decreasing until the bottom where user only know the stoichiometry about this chemical. But although this last one is the most inaccurate one, but we have this nice feature in our database where we can utilize the user's input, different information from our user's input the best, and we want to utilize the most from it. So when we have this data mining project over this summer, where we have a lot of students working with us, and we assign some of the chemical to our students, and they really help us to collect to data mining this chemical information. And the data source that we are using is the Omen Encyclopedia of Industry Chemistry. And some of our students also refer to Wikipedia, but I want to say the source of Wikipedia is also sometimes is pointed to Omen Encyclopedia. So this encyclopedia is a very comprehensive chemical information database, and if you search the chemical name, very often it will give you industrial standardized chemical report, where in this report is often contain a section called production. And for example, this is an example for a trichloroethylene ethylene. So it tells us what is the raw materials, what is the dominant raw materials that is used to produce this trichloroethylene ethylene. And they also have it also has another information, for example, enthalpy and entropy of the reaction of this process of this reaction. And we also collect that information. And because this is very important for us to model the heat requirement of the reaction. And they also have the market size of this process, and they also have byproduct and the co-product information. So we can fill in the number based on stoichiometry. And of course one chemical is not only made by a single process. So there are probably different synthesis pathway for one single chemical. So we also collect different process. We are not only limiting to our database to only one process. And we also record all of the different process we can find, and we choose the dominant process as our priority in the database at this point. So currently that's formed our database, and currently our database contains about 1,100 chemicals. And this database contains chemicals like poultry chemicals, very basic poultry chemicals, coloring chemicals, and ICIS global trading chemicals, and the European large volume chemicals, because those two categories of chemicals are very important in the market, and they are used very often. And we want to make sure that in our database we contains the chemicals that is very commonly are commonly used by our user. And so that we can make sure when user give us an input, we'll find those input chemicals from our database. And otherwise, we need to require another level of input from our user, which is not very ideal, right? And we also include some equivalent chemicals and also useful chemicals, because in those chemical list, in the useful chemical list, those chemicals are mostly very toxic and is most concerned by our, by CLiCC users. So we want to include that as well. And if our user directly input some useful chemicals, we will find it out in our database. And as you can image, since those building blocks chemicals are very commonly used in many reactions, and as we, when doing the summer, we assign those chemicals to our student, and our student will look up the chemicals reaction information from the Omen Encyclopedia. And to make sure that everything is linked together, we also assign the reactant that they find from the chemical industry report, and let them to collect the information from further chemicals that they already find, and so that we can make sure everything in our database that is linked. So that gives us a very nice tree structure of our database. It gives us our database have a very nice looking. As I just mentioned, I consider LCI as a tree structure database, and at the edge of the tree. Okay, so here I think I'm just going to show you the live demo of this. This graph is just one of the example of our current database, but we do have a demo at this point, I think. Are you connecting to internet?
Yes, but if you're going to share YouTube.
Okay, just one moment. Can we share this or not? I can go back to my slides, I think.
Yeah.
Should I stick with my?
Probably stick with slides.
Okay.
Yeah.
Are we sharing right now?
We can only share the slides.
Okay.
It doesn't seem like that.
So can you see my screen right now? Okay, good. So yeah, unfortunately, there is some problem of this conference software that we can only share the slides, but it's okay. So as I mentioned, this our database have a very nice tree structure looking at this point, and at the edge there are more complicated chemicals, and our user's input chemical will starting from the edge probably, and we will use our background database to link the user's input all the way up to some building blocks chemicals. In this example is the chlorine and ammonia, or something like water, sodium hydroxide. The size of the nodes representing the frequency of each chemical has been referred to by other chemicals in the same database. And at the edge are we want to make sure that we have very accurate LCI result for this building block chemicals. And we cannot see from this graph, but in our database currently we have some some nodes that is not connecting to the main island, meaning that those chemicals are disconnected. And if our user's input belongs to one of these disconnected chemical, we often call this chemical a small island, and the user input will end up with to a dead end, meaning that we cannot generate the full LCI for those chemicals. So, but it's not we have a few number of small islands. It's not big problem in our current database, but we are still working on it to eliminate those small islands, and so that we can make sure all of our users' input chemical will eventually link to some basic building blocks chemicals where we have very accurate LCI information. So here I just want to show you one of the demo example of how do we use our current database, and we selected one of the chemical is called dichloroprop. It is a very common herbicide and is used quite often in agricultural products, and it has this chemicals has some level of toxicity. And for example, if our user want to generate a life cycle inventory for dichloroprop, and they tell us, okay, this chemical is made by 2,4-dichloroprophenol and 2-chlorophenol acid, and we will fill in the number of these two chemicals by stoichiometry if the user can only tell us of the name of two chemicals, and if the user can tell us the reaction kinetics, we can generate the best case scenario selectivity for our user. And if they know everything about the first level unit process information, we will have a very accurate number here, especially about the selectivity and also co-product and byproduct. So in this graph, I'm only showing the raw material, which is a reactant, but in real case, we also have emission which come from co-product and byproducts. So, but again, in this graph, it's only about the raw materials upstream input. So we look up those two inputs in our database, and we find out, okay, 2-chloropropenic acid is made by 0.16 hydronic acid and 0.38 I-alanine. So I just want to mention, so every number here is scaled to 1 kilogram of dichloroprop, meaning that at the very edge of this tree, this is actually talking about if I want to make 1 kilogram of this desired chemicals, how much chemical we need here. This is not talking about making one chemical of the direct input. direct age is talking about making 1 kilogram of the desired chemical at the very bottom. So again, according to our database, to produce 1 kilogram, to produce hydraulic acid, we need to 0.22 methylene chloride, and to make methylene chloride, we need to 0.32 methane to produce 1 kilogram of dichloroprop. Again, just want to remind you, and also 0.38 chlorine. And on the left side of the tree, to produce this 2,4-dichlorophenol, we need to have a sulfuric chloride as input, and we also need phenol as an input. And the phenol is produced from cumin, and the sulfuric chloride is produced from sulfuric dioxide, and also produced from chlorine. And this number, again, is generated based on 1 kilogram of the desired product. And as you can see here, chlorine is referred 3 times here in this graph. It is referred by even more often in our full database. And so we want to make sure that, for chlorine, we have very accurate LCI number, which we do. We already collected the default building blocks LCI and from another report. And for each age node in the blue color is representing that for those nodes that we already collected very detailed LCI information. And our tree stopped growing from here, right, at the edge. And for those nodes in the gray color, we don't have, currently we don't have, those are building blocks, but we don't have a default LCI right now. We will either assign average organic chemicals at life cycle inventory for those chemicals for those building block chemicals that we cannot find life cycle inventory information, and also we are still working on it to collect very detailed LCI information so that we can complete the full LCI. And I'm sure for cumin and sulfur dioxide, we will have very detailed LCI information eventually. But for this chemical, and I'm really not sure, and we will eventually assign probably an average organic LCI for this chemical that is not very commonly used, but is still at the center of our database. So that's one of the example of our this is one of the demo of using our database. And again, as you can see, so this project is still in the preliminary stage, and we have been working on this project over this summer, and we have already collected a good amount of chemicals in our database, but there are still a lot of work to be done in the future. The first biggest thing is that we need to clean up the chemicals that are not connecting with the building blocks. The demo that I just showed you in the last slide is it's a very nice example that we can connect our desired chemical all the way up to some basic building blocks like chlorine, methanol, and phenol, cumin, right? But for some of the chemicals that I just mentioned, they are disconnected from the main island, and we want to eventually eliminate the small island. And also the second part is that we need to fill in the heat requirements, right? I just mentioned in our current database, we only have raw materials requirement, but heat requirements, although raw materials make the most contribution to the final impact score, but heat requirements for some of the chemicals, especially for polymers, for example, it might require a lot of heat and energy to produce polymers. So we definitely want to include heat requirements in our LCI database to complete the full LCI. And also, if you're familiar with life cycle assessment, we only have A matrix right now, right? It's a direct input and the output matrix. And we don't have B matrix, which is talking about the elementary flow of in LCA. So we definitely want to use we collected the byproduct and co-product information, right? But so we need to clean up the data that we collected and generate a matrix that is talking about elementary flow. And after we have once we have the A matrix and B matrix together, we will make a full LCI life cycle inventory, and it will support the use of other CLiCC module, and it will be accessible to all of our CLiCC users. So that concludes our current project. So just to recap very quick, and we create our database, which is able to generate chemical life cycle inventory with different level of accuracy based on our users' input data quality. And we fill the number with a stoichiometric approach, and it has shown a very good result in terms of modeling the quantity of raw materials input. And also the output of the LCI module will support the other module in the CLiCC project. and which is very important because the LSI module is located at the very beginning of the entire CLiCC project. And without a good, very good life cycle inventory data, the other module is running without any very good input. So it's not very ideal for the whole project of the CLiCC. So at the very end, I just wanna thanks all of my thanks our advisors. This CLiCC project and also this life cycle inventory project is under the leadership of Professor Mike from chemical engineering department, and Susanna also from chemical engineering, and also Sun Wang from Green School, and all of my colleague Jeff who was talking with me, and also Stefano and Yuwei and myself, and also Marvin who come from Art University all the way from Germany, and he's going back very soon. So we want to especially thanks for him. And also especially thanks to all of our undergraduate interns from chemistry and chemical engineering department over this summer. They really give us a lot of help during this summer in terms of collecting data. And they spend, as you can imagine, data mining from the chemical industry report is very daunting work. And they spend a lot of effort on this, and they make sure the data quality of our database, and also spend a lot of time in cleaning up the data that they collected. So we want to especially thanks for them. And because of the help of everyone, we are able to create this database, but we still have a lot of work to do. And so in the future, hopefully we'll come up with a very comprehensive lifecycle inventory database for chemicals. And this will be one of the largest chemical inventory database in the world right now. So that's wrap up our presentation for the lifecycle inventory module. And again, if you have any question, you can type in right now. And since we are recording this talk, you can direct your question to this mailing list. This is our CLiCC project mailing list. It's click at list.brin.ucsb.edu, and we will answer your question very as soon as we can. And just to remind you that we have 2 more webinars. We have the second webinar is happening in September 30th, right? And the last webinar is going to in October 7th. We will send out the webinar link to all of the participants. So thanks everyone. And if you have any question, you can unmute yourself and ask right now. Otherwise, we will wrap up our presentation, and later you can direct your question to our mailing list.
I just unmuted every external participant. So if you have any questions, we're welcome to hear them and try to answer it right now. Otherwise, like Ray just said, you can always email us on the bottom of the slide. Okay, if there's no questions, then this will conclude our first webinar, and we hope to see you again on September 30th. Thank you for your participation.
Thank you.